Hey folks, looking at Class 62, we're going to start talking about some springs. So we use a FET simulation here, and one thing we found was that it's harder to stretch a thicker spring with a higher spring constant than it is to stretch a thinner spring with a smaller spring constant. We'll get into exactly what spring constant is in a bit, but just for now, that's what we saw to start. So we created a graph. So I'll go through this quickly because I don't want to open up the simulation again and do this from scratch. We had the small spring on the left, if you recall, and the big spring on the right. I would recommend opening up the simulation if you're not really sure how this worked. Then we added different masses to each spring, 50 grams, 100 grams, 250 grams. Now to go from mass to force, we simply found the weight, so mg. So 0.05 times 9.8, 0.1 times 9.8, 0.25 times 9.8, and so on. All right? Then we use the simulation to find out how far the spring stretched. Not how long the spring was, but how long it stretches, elongation. And we took down that data as well. Notice how the smaller spring constant, the smaller k value, stretched more than the larger k value. Kind of what we expect. It's harder to stretch a spring with a higher k value, a higher spring constant. Then we plotted force versus elongation. Again, x is how far the spring stretches, not the length of the spring. Okay, it's just how far it's stretched. So we plotted these two data sets. We noticed that the slopes are quite different. But regardless, you should see that there was a linear direct relationship. So finding the slope of the thinner one, which was the shallow or the less steep slope, using rise over run, because we must use rise over run always, of our line of best fit, we got 3.16 newtons per meter, because it's always the y unit, which is newtons, over the x unit, meters. Now, the thicker spring, it looks like our slope was 12.5 newtons per meter. Now, in your own words, how does the slope, or excuse me, what does the slope represent? It just represents how much force is required to stretch the spring a certain distance. For example, 12.5 newtons per meter says that you must apply 12.5 newtons of force to this spring in order to stretch it 1 meter. All right? So the stiffness or springiness of a spring is referred to as the spring constant of the spring, which we abbreviate with a lowercase letter k. The stiffer the spring, the higher the spring constant. The less stiff the spring, the lower the spring constant. And it has units of newtons per meter. So what we just spoke about and what we just graphed was actually this thing called Hooke's law. All right, so Hooke's law relates the force required to stretch a spring to its spring constant. So this is the equation from your reference table. So Fs is the force applied to the spring, or the force that the spring is applying. It is equal to K, the spring constant, times X, the distance the spring is stretched or compressed from equilibrium. Now, I feel like equilibrium is just not a good word to use there, so let me fix that real quick. I think that's going to be actually pretty hard to do because I don't have my stylus in hand. I think what I want to say is natural length. So why don't you write that down there? I'm not going to write here. Natural length, I think, is a better word to use. Okay, I think equilibrium's a little bit deceiving. All right. So again, we just found the slope here. So let me get off of this for a sec. Anyway, so I said find the slope of the graph to the right. Again, rise over run must be rise over run using the line of best fit. Do not use the data points. No y2 minus y1, none of that. And we found that it was 66.7 newtons per meter. Now, notice that newtons per meter, that's also our unit for K. All right, so the slope of a force versus X graph is K. Okay, the slope of a force versus spring stretch or elongation is the spring constant. Okay, it's the ratio of those two numbers. So if a mass hangs from a spring of a certain, an object of a certain mass hangs from a spring, and the spring constant is 150 newtons per meter, what's the force pulling on the spring? How far does the spring stretch? Now, I will tell you, this was not a two-part question on the Regents exam. You had to know that the force pulling on the spring was equal to the weight of the object. So you had to know to do this whole mg thing, okay, to find the force. Then, for the next part, force on the spring equals kx. Well, we know the force on the spring is equal to the weight pulling on the spring. K is given to us, find x, 0.016 meters. This one here, you're given K and you're given the force, find X. Real simple. You have 0.17 meters. Now, I like this next question because it doesn't tell you any numbers in the question itself. You have to look at the picture. So from the picture, you have to realize that the x value is 0.1 meters. Why? Because that is how far the spring stretched. Again, that is what x is. The force pulling on it is given to us in the picture, 35 newtons. F equals kx, we get 350 newtons per meter. So 350 newtons of force is required to stretch that spring or compress that spring 1 meter.